Okay, guys, this is second part of a three-part series review for the exam tomorrow. We're going to do in this one the shear and moment diagrams for the beams, right? The beam bending, and we'll do both the analytical method as a function of x and the graphical method. Okay, so let's see the first problem. It's the problem 6.3 from the book. Oops, I use a blue color. Okay. And the very first step we need to do with the beam always is to find the support reactions, okay? And so I'm going to do it here, and this is my beam, and I'm getting rid of this wall. It's cantilever there. Let me first write the forces that I already have, which is 8. I'm going to skip the kips because they're taking too much space. But you don't have to write the kips in your problem. Depends on how important it is, how clustered it is, how obvious it is. Okay. If there are units changes, then make sure you put the units. Otherwise, when it's uniform like this, you don't have to worry about it. Somewhere at the end, I want to see the final result having units. Okay. So this part here, the continuous load, is really, we can draw it, but I'm not going to draw the arrows. I'm just going to draw in the middle, cross it, right? And that's going to be my force, which will equal 2 times the length, which is 6. So 2 times 6, which is 12. And finally, at the support here, we will have the force, and I'm not going to write what it is, and the moment. So let's look at the force. It's obvious that this force will be pointing up because there are all these forces pointing down. And so we have 12 plus 10 is 22 plus 8 is 30. So we see that this one's going to be 30. If there's any doubt about your reactions, you better do sum of x's and sum of y's and sum of moments, whatever you need, equal to 0, and then calculate from that. But I can see that this is an easy one, and we can easily calculate it. Same goes for the moments. They're all going to be going around this way, right? Around the support. And plus this moment that's going around that way. So we don't have to wonder what is, how are they matching up. They're all going to add up. So all we have to do is add up the moments for this whole beam, for this point, and that's how we're going to get this moment. We can see that it's going to be pointing in that direction, okay? And so let's just do that. This point I'm calling A, this point I'm calling B, and this point I'm calling C. So I'm calculating, so the same here, okay? This is B, this is C, and this is A. And so let's calculate the moment for point A, and I'm just calling that moment positive, so everything else will be negative. So basically, I'm just going to say whatever is the opposite to this moment, I'm going to throw away on this side of the equation. And so MA is equal to what? This force doesn't have a moment around A. This one has a moment. It's this distance is 3. Okay, so I'm going to draw my dimensions. Okay, so this one is 3, this one is 3, and this one is 4. And so now we have everything. So the moment of this force around A goes like this, so it's 12 times 3. So let's just write it 12 times 3 plus, it's not always going to be plus, but here it is plus. This force, which is 10, times the arm, which is 6, and plus 8, and then times the entire length, which is 3 plus 3 plus 4, it's 10. And finally, must not forget the moment, which is 40. And you end up getting that your moment around the point A, this reaction, moment reaction in A, is 216 kips foot. Okay? So I will be dragging that. I'll write here MA, and then I will be just writing the numbers everywhere else. So let me, oops, that's not a good one. It's really hard to draw on this because it doesn't slide so well. That's better. Okay. And so now what do we have? I'm going to use a different pen. I'm going to use a red pen. first we're going to make, because we're going from 0 to x, we're going to make a cut in the first section. There are two sections, this one and that one. And then we're going to make a cut in the second section. So the first section, I'll use a red pen, is going to be from 0 to 6. Notice that I didn't put here less or equal than. Just up to 6, but stop right before the 6. And then, because that's how we make these sections, only up to the section from the direction we're going to. And then when we make a section here, that bit will be included. So please mark this somehow in your work so we can see that that's what you're doing for this section. And so what do we have for that section? I'm going to actually draw that stump of a beam right there so that it's clear what's where. And so let's see what we have there. We have the reaction, which is 30, and this is 216. And then what else do we have? We only have a concentrated load. So I'm going to draw it like this, and this is how that beam looks. The load due to this is acting right in the middle. So if all of this is x, then it's acting, and let's back up a little. Let's draw the reactions. The reactions are, forces are this way, this we don't know, this is like almost, it cannot be more than 12, so it's going to be less than this. So the reaction will be actually going down. So that's my V of x. That's the reaction of the thrown away part of the beam when we made the section. And then there's going to be a moment. So if this moment is going, we're now calculating the moment around this point of the section. So 216 goes this way, 30 goes that way, and this little goes that way. So I think the total moment would be going in this direction. So that means the reaction moment there is this. It's a guess. If we guessed wrong, it's going to be something else, but we will keep track of it when we calculate, when we draw the diagrams. Okay, so now we have all the values. This amount here will be what? This amount here will be 2 times x, right? The whole part, so it's 2x. But the distance here will be x half, right? Because we need that distance to calculate the moment at this point. So let's write out the equation. V of x, that's the shear force in the cross section right in this internal shear force where we made the cut. That is equal to 30, it's pointing up, right? Minus 2 times x. And is there any other force? No. So that's our force, and that's in feet. Okay, this is how we write units in square brackets. Now let's write the moment with respect to x. The moment around this point of all these things. So the 30 will have a moment. It will be 30, it's in this direction, so it's positive, times the entire distance, which is x. Okay, then minus 216, right? Minus 216, because we said when it's in this direction, that's negative. When it's in up direction, it's positive. So minus 216, and now we have to count for this guy, which is 2x acting half of x away from that point. So that's then, again, minus 2x times x half. And is there anything else? No. So that means, I'm just going to keep writing like this. Let's group them out in a ascending order by the order of degree, or power. So 2 and 2 cancel, so we have minus x squared plus 30x minus 216. And that's in, that's in kip times foot. Okay. And so now I'm going to use an orange pen and do the same thing, but for this cut. So that means I'm redrawing the whole beam. I know it's a lot of work, but that's how it's done, if you want to do it right. So I'm redrawing the whole beam, but notice what happens now. Our cut is away from this continuous load. So now the length of the continuous load, continuously distributed load, is constant. It's 6. And here and we have this force of 10 kips, we must not forget it. So that's 10. Then we must not forget this one, which is 30, that's the reaction. And we must again not forget the reaction moment, which is 216. And so this force here, due to the continuous loading, is now again equal, as we did at the beginning, 2 times 6, which is 12. And we'll see where it's acting. We need to find the distance from here to the cross section to find the moment around the cross section. And we must not forget what? The force, which is resultant force there when we threw away the last bit of the cross section, and then the moment, which is this. Okay, and so we're writing these two in terms of all these guys. So now let's write what we need to do now. 6, and now I'm going to write less or equal. Here you write only less, here less or equal. Okay, x, and then less or equal, then 10. This means that x is between 6 and 10. Okay, and for that we have Vx is equal to, so now we're looking at Vx again, our x starts at the same place, but it goes up to here. That's our x. And I'm going to just try to be tidy and clean this up a little. There you go. So let's calculate. V of x is equal to, again, 30. Basically, you'll be copying this whole thing, minus, but now instead of 2x, you have 2 times 6, because it's not x anymore, it's 6. So it's 2 times 6, which is 12, then minus 10, that's this force here, and that's it. And so now the equation with respect to x is there any force here that depends on x? No, now it's constant. So all we have to do is add this up. 30 minus 10 is 20, minus 12 is 8 kips. Okay. Oops, I not just noticed that this is not feet, this is kips. Sorry about that. That's better. Okay, and now let's write the moment. That's the last remaining thing, and that's equal to what? Again, we have 30 times the arm, which is x. Notice it's the same as here. So it's 30x. What's next? Minus 216. Same thing, minus 216. Here we had the 2x times x over half. But now we don't have an x. We just have a 2 times 6. But now we have to, which is 12. We already calculated that. But now we have to find the distance of that with respect to the cross section. And that's going to be equal to what? It's this distance here. It's equal to x minus the location of that force, which is 3, right? This is this amount here is 3. It's the middle of the section. So it will be 12 times, and it's minus, so let me make this fat like the other forces. 12 times, and then this minus that. So it's x minus 3. Next force, the moment, is the moment of this force 10 around the cross section. So again, it's going to be the same. And the position of it is going to be x minus the position of 10, which is 6. So it's going to be minus 10, oops, and in the parentheses, I should probably write this a little better. So it's going to be equal to 10 minus, and then x minus 3 times, not minus, x minus 3. Is it 3? No, I'm sorry, it's 6. It's the length of this whole thing. So it's 6. That's better. And is there anything else up to here? No. So when you add all that up, let's look at the squares. Do we have a square? No, we don't have a square. Okay. because now we are done with everything. And so it's going to be just a function of x. So we have 30x minus 12x minus 10x. So it's going to be minus 8 or plus 8x. So 30 minus 12 and minus 10. And then is going to be minus, and here we have minus 12 times minus 3 is minus 36, and minus is plus 36, and minus 10 times minus 6 is plus 60. So we have 36 plus 16 is 96. 96 to 100 is a 4, and 116, so it's 120. Okay, and that's our result. That's the function, and that is in kip times foot. And if only I had room here to draw a free body diagram, that would be it. But because you're looking at it, what we're going to do, I'm going to erase it, this bit on the diagram, so that I can draw the forces, shear forces and moment diagrams, okay? Okay, so let's draw it. A little crooked, but it's going to be okay. So the first one, the force diagram, will look something like this. The shear force diagram, right? This is my x going in that direction. And now what do I start with? Well, it has to start with 30, right? Because that's the reaction. So it looks like this. That's 30. And I'm writing here 30, okay? And then how does the force drop down? So now I'm talking a little bit about also the graphic method. How does the force drop down due to just the continuously distributed loading? It drops down in a linear fashion but with a slope, okay? And so it's going to go to a certain point, but let's look at what the equation tells us. The value at x equals 0, when you substitute it here, you get 30. Sure enough, we guessed right. What is the value at the end of that location, at the end of that part of span? 6. So x is 6 there. So for x equals 6, this whole thing becomes 30 minus 2 times 6. 2 times 6 is 12. 30 minus 12 is 18. So from 30, it drops down to 18. That's slightly more than the half. So it's kind of like that, and I'm going to delete it just so that I have, yeah, around there. So it needs to go down there, okay? And that's 18, that point there. And so now next we would look at this guy, because now we want to go from 6 to 10, from 6 to 10. Now we have to plug in x there. But is there any x there? No, because it's constant. It's 8 kips. So we have to drop down by 10, which we already knew because there's this force here of 10 to the point 8. And from that point, we go horizontal. So this is 8. This force here is our 10 kips. And lo and behold, it matches up with this, because this has to come down to 0. Okay? Because this is hanging in the air and all these forces have to zero out. So this is 8 kips also. So that's how we draw the diagram. And I'm just going to maybe shade it a little, not too much, just so that it shows that that's our V. And I'm going to do this. And if I haven't written kip anywhere, I will write here square brackets and saying kips, but not in the middle, but on the side. Okay, so that's our shear force diagram for the bending, for the beam. Now let's draw the moments diagram. Okay, so I'm going to start from here. I know where it's going to go, but I'm going to leave it like this, kind of half, to leave space on both sides. And so let's see the equation. Okay, so the first equation is minus x squared plus 30 minus 216. So when x is 0, these two are 0, and it's only minus 216. So it starts from negative, okay? And this is minus 216. And then from there, how is it supposed to behave? What did we say? Now this is graphical deciding. If you have a slope in the shear, a straight line with a slope in the shear diagram, in the moments is going to be quadratic. Well, obviously it is. But how are we going to draw it from this point? Well, the values, if you look at this value and that value, they're positive but decreasing. And it's exactly what's going to happen with the slope for the moments. So from this point, your slope, there will be a slope. It's a quadratic curve. It will be positive slope, okay? So what does it mean? The positive slope, it means it's oriented somehow like this, but decreasing as we go from point to point. So it means it's going to level out towards horizontal. So it's going to look something like this, right? It will look, I'm going to draw a big line here, like that, but we are not sure where is it going to stop. Okay, so I'm just going to start it. Before I continue, I've decided how the slope is going to look, so I'm happy. But let me see what's the value here so that I can draw it and then at least a little bit to scale, and then I can move on from there. So the value there is x is equal to 6. So I'm still looking here and plugging in a 6 into this. 6 squared is 36. That's minus 36 plus 30 times 6 is 180. So minus 36 plus 180 is plus 144. Minus 216, so it's going to be still negative, and it's going to be 72. Okay, negative 72. So it's kind of somewhere here. So I know I'm going to kind of try to draw it like this. And that's negative 72. Okay, so this is a part of a parabola, but it's not, it doesn't end up straight here, okay? We don't know. Where is it going to be straight? What we know, though, here is that the rest of it, I'm going back to geographic, because the shear is constant, this line here will be slope, but a straight line, okay? And so for this section, we need to look at this equation and plug 6. When we plug 6, we will see we get 72. So 6 times 8 is 48. Minus this is minus 72. So that's matches. So it's right there. And we should have known that, because the only time this changes is if you have a moment on the beam somewhere. But we only have a force. So the shear diagram will have a jump, but the moment will not have a jump. They will be at the same point. However, something will change. Here we had the curve, quadratic. But now we're going to have a straight line. And let's see where that straight line goes. So plug the 10x, so it starts from minus 72. And when you take this last bit, last value, the 10, and plug it into moment equation here for that span, you get 80 minus 120, it's 40. So that's just about half of that value. So things are getting small here, okay? And now if you notice, that is going to just follow and hit this. Oops, that last bit wasn't so good. I'll try to do it better. Okay. All right. So that's a straight line, quadratic, and this is linear. Okay, and that's minus 40. And it should match because that's the moment of 40 we have there. So everything's perfect. We did a really good job with this one. Okay, and I'm marking it here as the moment diagram. And that's it. That's all there is to this problem. Now we have a different problem, 620, where we were supposed to do the same thing, right? Only all the loadings are moments, and I've done something similar, but I want to make sure that everybody understands that you still, I know you know, but you would be surprised what I see on the exams, that even though they're moments, they will still be reactions, force reactions in both the supports, because that's the kind of support we have, okay? And the moments, everything is written in terms of M0. I'll just call it M. Let's not even call it 0. This just means that it's a given, it's a number, and all the lengths are A. So that makes it really easy. So let's look at the beam when we look at the supports. What I have here is this moment, and I'm going to draw it like this so that I remember where it's from. And that moment is in opposite direction. So they're all M and M. And here we have, there are no horizontal forces here. We don't really care about them. So these moments, there are actually, but we don't care about them. So these two forces, this one, this is the point A, so I'll call this FA, and I'll call this FB, and these are my reactions. And so we see the FA, and because these two are the same, they're right in the middle, we have a symmetric case, so we know that FA will be equal to FB. We don't even care what they are. We know that they will be equal. But from the sum of moments around, let's pick a point A, and let's pick it like this to be positive. From that equal to 0, we can calculate how much these reactions are with respect to M and A. Okay, so don't get confused when you have a situation like that. Just remember which of those letters is something that's given, that's a known value, and which is the one you have to find. So the FA and FB, I have to find because I've just said these are the supports and I don't know how much they are. they are. So what do? Moments around A, if this is positive, would be this moment is positive, so it's equal to M, and but this one, the next one that comes by, is that one, so it's negative, right? So it's minus M, and then this reaction here creates a moment which, we forgot that moment, didn't we? So the first moment is M, positive, right? The next one is also positive, so it's plus M. So M plus M, and this one's negative, minus M. And then we have this reaction, which is FB. And it's FB times how much? 1, 2, 3A. And that's equal to 0. And from that, we can see 2M minus M is M. Okay? So our FB is actually going to be pointing down. So just for the purpose of simplicity, since it's not too late in the problem, I'm going to change the direction so that we don't have to worry about that later on. Although I suggest if it's just any little bit more complicated, not to do it. Do not change the sign because you can get messed up. But 2M minus M is M is equal to FB times 3A. So my FB is going to be equal to M over 3A. So now we know what FB is, and that's also equal to FA. And these are our supports. Okay? So each support has a force equal to M over 3B, which we kind of could have guessed. All right, so now what's the next step? The next step, as we said, is we have 3 sections, so we need to draw these lines down there like that and start working on section by section. So red, okay, goes from 0 to A. So that's our first section. And so the shear forces, I don't have to write V of X. All the V of X will be constant throughout. We see that already because there will not be any more forces added along the way as we cut the new sections. So the only thing that really will be changing is the moments. So what I'm going to do is I'm going to do this a little bit different. I'm going to how I'm going to write it, I'm going to write it like this. I'm going to write it like this. From 0 to 3A, the entire span, V of X, all the way through is constant. and equal to one of the supports, which is this. I'll just write it right away. Well, let me write one of the supports. We started from left, so we're going to do from left, okay? It's equal to FA, which means it's equal to M over 3A. So that's always going to be true. So I can just draw it right away, and it looks like this. This is X, and the reactions, this one is going up, that one's going down, so I know it's going to look like this. And I'm going to mark this as M over 3A, and this is M over 3A, and this is our moment, and this is shear diagram. Done. Okay, so now all the work we're going to do now is going to be for the moments. So let's write one by one using different pen. I'm going to use an orange. So now we're going to do from 0 to X to A. That's our first one. And the moments will be, what do we have? We have a force FA. I'm going to draw. So this is the first one. The first one. And so what do we have? Never forget. We have a reaction here, okay? So that's equal to M over 3A. And then do we have anything else? We have this moment that acts right there, which is just M. But here we have reactions, right? We have the V of X, which is always going to be this. And then we have a moment that is acting in which direction? Probably in this one. So that's the moment M of X we're trying to calculate. And so that one, M of X, is equal to what? This force, which is M over 3A times the X. Okay, so it's, and is it positive? Yes, it's up. And the way this moment and that moment act together is positive. As we said, positive convention. So M over 3A times X. And then plus M. That's the equation for this span. Okay. Now, when we make a new cut for this section, we again draw the whole beam. Oops, maybe not all the way that way. To the cut. And now, again, we have to repeat this several times. Don't be overconfident. It's better that you repeat it instead of guessing on the exam. Okay. And so this is X now. Again, we just have this force, nothing else. But we have this moment. That's, I forgot to draw it. That's that moment here. But we also have these two. And at this cross section, we only reached up to that one. So that one also has a moment. Okay, starting at around that point. So that's also moment. And again, we have the V, which we don't care about because we already calculated it. But then we have the M of X. And now the M of X for that section, the section is now not 0 anymore, but A, X. And again, I should make sure that you don't think this is equal because we only go up to A, but not including A. But now we're including A. So here we do include A. And then up to 2A. And now we write the moment, okay? So the moment of X will be equal to, and again the same thing. It's going to be M over 3A for this force times the X to that point. So it's going to be M over 3A times X. Then this moment is just plus M. Then that moment is just plus M. And that's it. And so that equation is, I'm just going to rewrite it, is M over 3A X plus 2M. You can pull out M's, but you're not gaining much. It doesn't really matter. So, or you can write it maybe as M and then X over 3A plus 2. So when you substitute X, you'll just get a coefficient and multiply. either way. And then we'll have the last one is from 2a, but now we include the equal. And again, at the very end, we do include the equal all the way up to 3a. And for that, our m of x is equal to what? So now again, we have to draw the last one because we're making a cut here. So the last one that's also m. But now at this point here, we have the m in the opposite direction, okay? And then here again, we have in the section, we have a shear, internal shear, and internal moment that I'm going to again write like this. And that's going to be m of x. That's the one we're trying to calculate. So let's add things up. So again, this is x. And again, what positions they are, the moments are, doesn't matter, they add up. So that's pretty easy problem. M over 3a times x plus m minus m. Okay, because this one is the opposite direction. And there's nothing else. And when you add all that up together, you get these 2 plus m, so it's 2m minus m is just m. And then if we pull this m out, we'll get x over 3a plus 1. And here we had plus 2. And so now what we need to do is draw a moments diagram because we've already drawn this one. So I'll have to do a little bit of erasing here just to make it easier for me to draw all this. Okay, green pen to make the lines, and almost there. Okay, so let's draw now the moments diagram. What do we see from the first span? That the moment at x equal to 0, when you substitute 0 here, is just m, okay? And it's logical because that's the real moment that we have in that support. So it is plus m. So I'm going to draw something that looks like this. Okay, and it will be plus m. So that is just m, okay? And then we have from that point on, because everything is straight in the shear, you know it's going to be declining down. But how far with what slope we got to see here. Instead of doing that, let's use the equations. So when x is equal to a, we get ma over 3a. So it's m thirds plus m, that's 4m over 3. Okay, and how did I get that? Because I'm supposed to have something a little different. So let's calculate it again. So m over 3a times x and then plus m. And so when x is equal to a, this is 1/3 plus 3/3 is 4/3. So I'm right. This should be a 4/3. Hmm. I know where I made a mistake. my forces right here. So yes, all this is correct. However, they're both, yeah, when I was, you see what happened? This is a good example. When I was changing the sign, I totally screwed up. So let's rework it again, okay? What I need to have actually is these two forces to be opposite. And if you look at how the moments are applied, that's exactly how it should be. So let's rework the forces again. This force should go down, and that force should go up. I don't know why I don't follow what I already do, you know, if I prepare. I get excited. I want to do my own thing all over again. So from the forces, we don't see that they're the same. Actually, the way I imagine them is the way I assume them. I wrote, and I'm going to write it properly. That's what happens even when you have a very simple case, if you're just going out like headless chicken, just like I did. So let's just write sum of y's is equal to 0, and then write the forces as they are. Let's not say that they're equal because we're guessing. So we'll have that the way I wrote it is FB minus FA is equal to 0, and then they will be equal, okay, but not for that reason. I'm just looking at how the moments are applied. This moment will try to lift this support. This moment is pushing this beam down, which means it's pushing down on this guy. This moment, so both these moments are pushing the beam down. So this guy will want to go up, but this guy will want to go is being pushed down, whereas this guy is being pushed is pushing back up. Okay, um, so again, when the beam is pushing down, rotating this way, the support is going down. So let's see if that's correct. So now that we write all this, the minus sign is correct here for FB. We get that FB is equal to M over 3A, and FA is that's equal to FA. That comes from FB is equal to FA. But notice the way we wrote signs, they're the opposite signs, okay? They're equal in magnitude but opposite in signs. And so now it makes sense that our force diagram is actually going to look like this. If I erase this, I can switch it over. Don't kill me, okay? I don't have to change anything except these things. And where I write my x-axis. So actually, because this is negative, it starts from 0. So this is my x-axis. And the forces, this force is going down, and that force FB is going up. And now we're good. Okay, and this is x. And that's my shear diagram. So this is negative. Negative M over 3A, and this is negative M over 3A. Good, okay? And so we're good now, but that's where I noticed I made a mistake, because you know how? When I was adding these things, when I wrote this equation here, I noticed that that something should be positive instead of negative, and negative instead of positive. And so what should be negative? When x is 0, we still get the correct solution, even though for the moment in this span, right, for this section, even though actually this guy is negative. So this guy will be negative throughout, and that's where my mistake was, okay? So there will be a negative here and a negative there and a negative there. And I can properly write this for you so that you're not panicking. Oops, this is a big one. So minus m over 3xa plus m plus m. And so that would be equal to, here, equal to, this is 2m, right? So we take the m out and we get minus x over 3a plus 2. And here we get minus x over 3a plus 1. And that's much better now. Okay, so now when you go and start plugging and chugging, in the first span, x equals to 0, m is m, moment is just ends up being m. When you plug x equals to a, you plug it here, you get minus m over 3 plus m. And so sure enough, that's how it drops down to 2/3. But just in a straight line, because this is a constant function, the shear, right? So this is 2/3 m right there. And then from there, let's see what happens next. Okay, what happens next is from span this to that, we need to have a jump of a positive moment. So now that goes up again by the same amount as this, by m, because look, this guy comes up and adds itself up. So 2/3 m plus 1 plus 3/3 m, which is a 1m, is 5/3. So this should be a 5/3 m. And let's see when we plug a in this equation, beginning of the second span, do we get the number? So we plug a here, we get a and a cancel. You get minus 1/3 plus 2, which is 6/3, and sure enough, you get plus 5 thirds m. And then in much the same fashion, when you substitute 2a into here, you get 2 minus 2/3 plus 2, and they should come down to 4/3. Same slope, because nothing has changed here. So you draw parallel this and that. And then this point here is what? It is 4/3 m. Okay, so it's like a seesaw, but it's not, doesn't come down to the same thing. And then last, again, we have another moment, but now it's being subtracted. So we're not adding it up anymore. Now we're going to go down by m. 4/3 m minus m is 1/3. So it should come down to 1/3, which is about this much. Okay. And that should be 1/3 m right there. Okay. And let's calculate if that's indeed the case. That should be the value at the beginning of the last span, which is this value. 2a, and you plug it in here, so it's 2a by 3a, so it's minus 2/3 plus 1, and sure enough, it is plus 1/3. And when you finally look at the last bit of this last span, which is 3a, you substitute it here, minus 3a over 3a is minus 1, plus 1 is 0. So sure enough, it does come to 0. Do we have a moment here? No, so it cannot be anything else but 0. Oops, that's constant. I need to figure out how to. It's hard to draw this, okay? Hard to draw straight lines on this pad. But that's a straight line, so all this is linear. Okay? And that there is 0. And that's my x. And so that's our moments diagram. Alright? That was that problem. So our last problem is problem 626. We see we have a triangularly distributed load, so basically decreasing distributed load. We have two supports. Don't worry that this one is sideways instead of vertical as we're used to, because it's the same thing, it's a pin support. And then we have a moment right at that support here, which is 1,500 pound-foot. Well, since this is in kips, let's just make it easier and get rid of all those pounds, and we just call that 1.5 kip. Foot. So now everything is in kips and in feet. Okay. All right. So what do we do first? As usual, supports. Okay. And so my beam looks like this. And we have a support here and a support there. Now let's consider, is it up or down? Well, this load is loading it down. It looks like this one's definitely going to be up, so it's resisting in the opposite direction, so that's going to be a YB. And this one here, we have a moment going, pushing it down, rotating the beam this way. So that means it's going to try to, the force here, the reaction should be down, negative. Okay, so I'm going to change that. I might be guessing wrong, but now is the time to change before I decide on all the other things. Okay. And then I'm going to have a moment here. And again, I did it wrong. It's a wrong direction. It's pointing in this direction. Okay, and that's 1.5 is the moment. The force, we don't know what it is, but I'm going to call it YA. And we have the force due to distributed triangular loading, which I drew badly, like this. The force will be, I will just move this guy out of my way because I need space there. I will draw it here. And it will be middle of here and the middle there. And we all know that it's really going to be at one third of this, right? Which is the force here. The amount is 3 kips per foot times 6 feet, and then half of that because it's a triangle. And that's equal to what? 18 divided by 2 is 9. So that's 9 kips is this force, okay? And so now we have a free body diagram for this beam. I like to draw the given things a little fatter. I mean, all the forces, all the loads a little fatter, and that's it. And so let's do it. This is 12 and this is 6. So sum of y's is equal to 0. From there, we see that we have minus ya plus yb, and then minus 9 is equal to 0. And then for moments, around which point we're going to do, let's do moments around point A. Might as well. So we get rid of one of the reactions. So it's a moment around point A, and I'm going to use this as positive. And so let's see what we get. This moment is then positive, as we said, right? I drew it poorly. So it's going to be 1.5, just as it is. And then YB is in the opposite direction, so it's minus YB times the arm, which is 12. And then the distributed load is in the same direction as my plus, so it's going to be plus 9 times this whole length plus the third of that. A third of 6 is a 2. So 12 plus 2 is 14. So it's going to be 9 times 14, and it's going to be plus. And that will be equal to 0. So when you work this out, you will get that the force YA is equal to, I'm sorry, a force YB is equal to, from here, it's 9 times 14. I just calculated it, and it is 10.625 kips, okay? And then the YA is equal to minus, when you substitute that, so YB is this, minus 9, okay? And the value is 1.625, and it's just 1.625. So these are the values, the supports, but notice this is, and the directions I chose were correct. So the values are like this, but this one's negative, that one's positive. So that's just when we start drawing the shear diagram that we remember that, okay? And then next step is to start drawing our sections. and writing the shear moment diagrams. Okay, so let's do first the shear. Let's do first, we have two sections, right? So I'm going to cut, this is the first section, and I'm going to write for 0 to x to this point, which is 12. This is all in feet. We have what? That the v of x is equal to, we're looking at this diagram here, the forces are pointing down, up. You will have this diagram here. I just don't have enough room, so that's why it's kind of awkward. We're looking here and there, but you will actually have this diagram down here. Okay, don't draw it up above, draw it right below. The force is, for this span, just this YA. That's it. So it will be minus YA, nothing else. And that's equal to minus 1.625. The moment for that section, well, let me draw it. Okay, so here we have this force, which is 1.625. That's what we had there. And we have this moment, which is 1.5. And then that's our section. There's nothing in between, right? And all we have is the, again, I keep making this mistake. It's pointing down. And so this force will be pointing up, that's the v of x, and the moment of x will be pointing like this, mx, for that cross section at that point. And so now we're calculating for that point, the moment of this force is negative, so it's negative 1.625 times, this is x, right, and plus this. And so we can see later when we calculate, when we substitute x, we get the right stuff. Okay, so everything is in good shape. And then let me take the orange again, might as well. Let's draw what we get for from 12, for when x goes from 12 to 18. Okay, so that's the next span. Our Vx is now different because this is the section we are taking. This is the same, 1.625. The moment is the same, 1.5. This is x. Okay. And the only thing we've already drawn here, there's nothing here. But now we have the triangular load, which is kind of awkward because you see now we have actually a trapezoid. So where's the centroid of this trapezoid? Well, we know that the centroid of the trapezoid is right in the middle. So do we want to do it that way or we want to do it some other way? I don't know. We can do it, we can divide the trapezoid in two. And so the bottom part is rectangle and it would have the force pointing down, and the top part is a triangle, but now the centroid of that would be a little bit this way. It's a 1/3 from that side. So that would be hard to calculate. But I know that the centroid of this is along the median line. But do we even need the centroid right now for the v of x? We don't, okay? So we can just write v of x as it is. It will be this amount, it will be the area of this trapezoid. And the area of trapezoid is the this side plus that side, okay, divided by 2 and times the distance. So the distance is x. This side plus the big side is 3, right? So it will be 3, and then plus the little side is something smaller, and we decide that from 3 by 6 from the proportion, right? So we have 3 over 6 is the same as this distance here, and I'm going to call it the little p, okay? this distance here versus, I'm sorry, this distance here versus the height there. So I'm going to call this little distance here a P, and that will be what I'm looking for, which is Y, I suppose. Okay, and so we know what P is. That's the whole span minus X, right? So from here we get that our Y is equal to 3/6 times P times P, and P will be, I will write it again, is equal to 3/6 is 1/2 times, and we said the P is the whole distance minus X. The whole distance is 18 minus X. Okay, and so that's what I put here. So it will be plus that distance, which is 18 minus X, and then all that with half divided by 2. And that's the area of this whole thing, okay? And now that's equal to, so we kind of have to calculate it, right? It's equal to, we got 3 here, this is plus, 18 over 2 is 9, minus 1/2 of X, and all that over 2. 3 plus 9 is 12, over 2 is 6, and then minus 1/4 of X. And so now that's our equation for V. And now we have a harder job to find actually the centroid of this. Where would the centroid of this be? Well, the best thing would be for me to use this area here to just draw it bigger so that we can actually work on it. And not just that, but steeper so that I have room to act. That's better. Okay. So we know that this distance here, we've already calculated it, right? We know that that distance is P. Okay. So what we know is the Y, right? We said that this little guy here is Y. So that is this guy. Remember, that's the Y and that's the P, this here. And so this is now Y. This is the part we care about. And we don't care about this one. So the rectangle will have a centroid right here, and the triangle, I'm not going to draw the lines that I usually require to draw because we know it's about, it's at 1/2, I mean 1/3 of the height, which is right here. Okay, and so let's find out. This is Y. Okay, Y is equal to 9. I'm just calculating from here. Is equal to 9 minus 1/2 X. That's the Y. And we don't care about P. And so this is Y also. How much is this? This whole thing is 3, right? So then this amount here would be, we don't even care that this is Y. This whole thing is 3. This whole thing. All we care about are the horizontal locations. How much is this and how much is that? So this one is going to be equal to, we're counting that from X. So basically X ends here. That's X. And the location of this is at 12. So now we can say that the centroid for this guy is, so the centroid for the rectangle is at X minus 12. That's the amount of this, right? And then half that. So it will be X minus 12 and then plus X minus 12 half. Plus X minus 12 half. That will be the distance from here. But we really need it for this location here, right, where we are calculating the moment. We already calculated the v of x, but we are calculating for this point. So really all we have to find out what is the distance from here to there. I'm going to use a different pen to make sure that that's clear, a violet pen. So we're looking at this distance and at this distance, okay, because that's where our cross section is, right there. And so that should be easy, okay? So I'm going to delete this and write it again, because I'm sure I made a mistake. I didn't really prepare this. I didn't have time, so I have to solve it as I go, okay? Which I know you don't like, but this is real life. This is how you're solving problems, okay? So the rectangle is at the centroid of the rectangle with respect to the location of it, with respect to this cross section here. It's just this amount. So how much is that? It is the whole distance, right? So it's the whole distance, which is x minus 12. So now we got here. And then we have to subtract a half of that. So minus x minus 12 over 2. So something minus a half of that is a half of that, right? So it would be a half of x minus 12, which is 1/2 x minus 6. And so that's our value for the location of the centroid. So let's start writing the moment equation, and then so that we don't lose track of why we're doing it. So moments for that cross section of this force in the support, 1.625, okay, would be, again, the same is, and it's pointing down and not up, okay, minus 1.625x, and then this moment is again plus 1.5, same as in the previous one, but now we have to account for the moment of this. So this guy, the rectangle, will be having one force going down, and the triangle will be having another force going down. Okay, so now we're doing that. So the force going down from the rectangle is the area of the rectangle times this distance. So I'm going to write here, and let me see, is it a plus or a minus? Well, it's going down, okay, on this side of the cross section, so it should be negative. So we're going to have minus, and I'm going to write each one in one line. Or maybe I could try here. Minus the force, which is what? It is this length times the y. The y is that. And the length is x minus 12. So it will be x minus 12, right, times the y. It's this much. So that's just the force of the rectangle. And then times this guy, which is 1/2 x minus 6. And then we say minus, so this whole thing is just a rectangle. See how complicated it is? And yes, it's of the third power, okay? And then we have the same thing from the triangle. And the triangle is now even more complicated. The area of the triangle would be the same as the area of the rectangle, only times 1/2. So the only question is, what is the length of it is the same, this side is the same, but the height is not the same. The height is not y, it's 3 minus y. So where we had the y, we're going to write 3 minus y, and the rest is the same. So 1/2 times the length, which is the same as for this guy, which is x minus 12, then times the height, which is 3 minus y, 3 minus y, and we said y is this. So 3 minus 9 plus 1/2 of x, that's the area, and then times this distance, which is 2/3 of that, look, 2/3 of this length. So it's 2/3 of that. I'm sorry, 2/3 of the length, which is of the length of this structure here, which is x minus 12. Okay, just like we did here, a half for the rectangle. And that's complicated. And now I'm not going to sort it out, but I know how the graph is supposed to look, so I'm just going to sketch it, and you sort out the math, okay? And what I'm going to do is erase this so that I can quickly sketch out the graph. Okay, so let's sketch the 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 shear forces. Okay, we wrote shear here and there. And start from the beginning. It's going to look something like this. I'm going to mark this as an X, okay? And what do I have? Here at the supports, I have YA, which is kind of small, and the later stuff will get bigger in this direction. So, and it's a negative because it's pointing down, so only this amount here goes there, but it's constant all the way. You see, there's nothing else, no forces, until we get to YB. And so that's minus 1.625. And then what do we have? Well, we have the reaction. It sends it up, and quite a lot. It's by almost by 10. It's exactly by 9. So it goes up by 9, and sure enough, because YB is this amount, right? So YB and YA, so it goes up by 10,625. So 10 minus 1,625 plus 10,625, it's 9. So it will end somewhere here at 9. Okay, and then from there, if we had the continuously supported, continuously distributed load, then it would be parabola. It would be a slope. But because we have a triangular, it's actually a parabola. So it's the second power of x. And sure enough, we have the second power of x. So it looks like this. And where does it end? When you plug in x equal to 0. Now, how did I get a 6 here? I'm supposed to have, well, okay, I guess I'm not going to be able to figure this out right now. I have mixed something up here. Let's look at the Vx. The Vx is the x for this here would be equal to, oh, I forgot the force, of course. Look what I forgot. I forgot to account for YA. So somewhere in here should be YA. And because y is negative, it's going to be minus 1.625. Okay? And once you sort this out, and then plus that force, which is YB, which is 10,625. So when you put all that in here, with this, it cancels out. So it should be all okay. So we go parabolically straight down to 0. Well, not straight, but parabolically, okay? There's a curve there. Okay. And so this is a 0, and that's my graph. And this is also minus 1.625. And so that's my V. And the moments will look something like this. I'm not 100% sure that the numbers, I'm not going to calculate them, but I sort of know how it's going to look. It's going to look exactly like this. I'm going to use the graphic method now, right? I'm not going to ask you to do it on the exam, maybe this bad, but I just wanted to show you how difficult it can get when you're calculating all this, but how you should get and do it. So what do we have here? We have a moment right there. It is a support, so this force doesn't have a moment around that point, but we have a moment. And so when you look at the moment reaction, when you put x equals to 0, you'll get 1.5, which is exactly the amount of the reaction. So it's positive, so it's somewhere up. It's very small, right? 1.5. And then because this is a completely constant shear force, we're going to have, but it's negative, negative and constant. So here we're going to, from this point on, negative and constant slope. Negative slope means going down. So negative slope and constant. And it will be going down all the way in a straight line. Okay, so this is 1.5, and it goes down to which to how much when you substitute. So this end of the first span should tell you that the end is 12. So when you plug 12 here, you should get, when you add this up, uh, minus 1.625 times 12 plus 1.5 equals minus 18. So that's that point. And then what do we have here? We have the force, but we also have the change in a slope. It's not straight line anymore. Now we have a quadratic. So if it's quadratic in the shear diagram, it will be to the third power. And sure enough, there's an x, an x, and an x. So it will be to the third power, cubic. And where does it have to end? It has to end at 0 because we don't have a moment here. So I know that it's going to look something like this. It looks like it's a quadratic, but it's actually not. This is cubic. And this is a linear. And the other guy is, the shear is constant, and this is quadratic. So in an exam, depending on what I ask you to do, if I ask you to write the equations with respect to how these guys, how the shear and moment change with respect to x, you'll have to write all these equations. But if I don't give that to you, all you'll have to, well, you'll have to calculate the supports. Okay, once you calculate the supports, none of this will exist, only what I just wrote here. The only thing that will exist on your diagram now will be all this, exactly as I wrote. So this has to be present, and I want to see, to make sure, even if you drew it poorly, I want you to write what kind of line is this. This is a constant, that's a quadratic, that's a cubic, and that's linear. So if you haven't learned these expressions by now, you better do it now, because I want to see it on the exam. Okay, this is how you solve this problem. And there's a little bit of shading just to show that this is below and this is above. All right, mark all the points with their right values. And that's it. And I'm going to try to record one more, but I don't know if I'll have energy. Okay.